Hello everyone, welcome back for the part two of our dendritic modeling workshop with Lamar Makarov. In the second part, I'm going to discuss about Dendrify, which is a package I developed during my PhD for creating SNNs that capture essential dendritic properties. In contrast to part A of our tutorial, where Aman focused a lot inside the biophysics and let's say the biology of the neuron, here we have a different perspective. We're simply trying to start from a premise that we have simplified neurons, point neurons that are commonly used in the SNNs, and how we are going to make them more realistic by adding some simple properties that the biological neurons have. So, sorry. So, if you ever Google about neuronal anatomy, how a neuron looks like, you're going to see a picture like this one. You're going to see a huge soma, a huge axon, and some small dendrites just to capture that we have some dendrites. And this kind of indicates that the focus has shifted away from dendrites when it comes to our understanding about neurons. But the reality couldn't be further apart. Dendrites can occupy up to 99% of a neuron surface area. They are technically a neuron is its dendrites, and there's a lot of things going on inside these fine structures that in current SNN modeling they are going unnoticed. So early models totally ignored dendrites, and they focus primarily on what happens at the soma of a neuron. Thus, the point neuron model was born by McCulloch and Pitts back in 1943. This model is essentially trying to capture the thresholding that takes place at the soma when a certain threshold of voltage is crossed, which is a decent model. It's not a bad model, provided that dendrites are just passive receivers of synaptic inputs. In other words, if dendrites don't contribute much to input processing, having a simple point neuron model is sufficient to develop a network that captures a correct behavior, let's say. However, dendrites are way smarter than we initially thought. Here is an example of a C1 pyramidal neuron, and with the color code, you can see different mechanisms that exist in different parts of the dendritic morphology. And like soma, dendrites can generate spikes, but unlike the soma, they're much more heterogeneous. For example, they can have sodium spikes that they last for a couple of milliseconds. There are calcium spikes that they run about tens of milliseconds. We also have NMD spikes that also have long durations. And you can see that in different parts of the dendritic morphology, we have different combination of spikes, or let's say receptors, voltage-gated receptors that are combined to generate different outcomes. And here you can see this is from a neuron from a neuron model that how the different voltages propagate along dendrites to result in dendritic, in somatic output. And you can notice here that when we activate this part of the dendrite and this part of the dendrite, we have some initial dendritic spikes that are generated distally. And then because there's some extra input proximally to the soma, this proximal input helps the dendritic spikes to propagate along the soma and the axon. And additionally, another thing you can see from this very beautiful simulation is that dendritic spikes do not have a single direction. They don't go only from the dendrites to the soma, but they can also backpropagate back to other dendrites. For example, here you can see that after the axonal spike is initiated, there's also spikes that backpropagated to the basal dendrites of this neuron. All these mechanisms, in conjunction to the morphology of dendrites, they generate a very heterogeneous and dynamic repertoire of functions. And you can see, for example, here these are some specialized experiments. I'm not going to delve into them, but you can see how the input output function changes as a conjunction of different combinations of channels that exist on the dendrite, or how the diameter affects the input output function of the neuron, the branching points, the distal the soma. So, um, in other words, to put it simply, neurons are not just they cannot be adequately modeled just by a point neuron model. They do have dendrites, and the dendrites can also express a wide variety of mechanisms and channels, and they also have different biophysical and structural properties. And all of these in conjunction, they allow to have a very heterogeneous and diverse mapping of input to some neuronal output. And another very interesting thing, in my opinion, is that different information streams they usually go to different dendrites. For example, here you can see from a cortical neuron that usually information that is more data specific, that captures, let's say, more what happens in the visual cortex, usually go to, sorry. So usually more visual information, or let's say more data-like information goes proximally to the dendrite, whereas more contextual information, such as inputs from the hippocampus or other brain regions, they go distally to the apical tuft of a neuron. So you can see that different pathways can go to different dendritic branches, where we also know that they might express different mechanisms. So, the central question of my PhD, what is the role of dendrites in brain functions? Not a very simple question to answer. And when I was starting my PhD, the default model, let's say, to study dendrites were the biophysically detailed models that Raman described earlier. These models have very accurate um, biological properties. They capture the morphology of real neurons. They do express the channels that are present in the biological neurons. They are highly realistic, very accurate, and they allow for low-level experiments such as pharmacological interventions or adding various blockers and stuff. However, they are very inefficient because they require multiple of equations to describe all these properties. They're not so easy to run in scale that's required to create large networks. They're also very complex to develop. They require a lot of data to make sure that they're biologically accurate, and they're also not so practical to use in networks. On the other side, when I was starting my PhD, another actually the default neuronal model used in SNS was the point neuron model, which is very lightweight. It's very easy to develop. It's tractable, and it allows to scale into large networks. On the other side, it's less accurate. It's overly simplistic when you want to take dendrites into account, and of course, it has no dendrites. So then we decided in our lab, why don't we try to create something in between, something that is trying to combine some of the good characteristics of biophysical models with the advantages of point neuron models. And that's how Dendrify was born as an idea. So, in a nutshell, Dendrify is a theoretical framework on how to translate some complex biophysical, biological properties of real neurons into more simplistic SNNs. And also, it comes with a Python library that works with Brian 2 and allows to actually create these models in Brian 2. But some of the principles that we're going to discuss today are not only confined and can be used with Brian 2. You can also, if you are a good programmer, you can try them and implement in NumPy, in PyTorch, or the simulator of your choice. So the first feature we try to implement in Dendrify is the anatomical simplification. We don't use any fancy algorithm to make the morphological reduction. We're just making the hypothesis that can we, instead of using multiple compartments as in biophysical models to capture the entire complexity of the dendritic tree, can we do something similar by utilizing just a single node to capture entire neighborhoods of the dendrite. For example, here we have again a pyramidal neuron that has the soma here, the basal region, the proximal apical region, and the distal tuft. And in a very, very simplified way, we propose to extend the point neuron by using, for example, another compartment that captures the inputs that go inside the proximal region and the inputs that go in the distal region. So from a biophysical model that would require thousands of segments, we just go to a far more abstract model with only three compartments, but maybe this model is good enough to capture some key dendritic processes. And another feature that was implemented in Dendrify is that I guess most of the audience that is present is familiar with the Hodgkin-Huxley model. Also, Raman described it in the previous presentation, which is a state-of-the-art model on how to describe realistically the action potential dynamics. But as you notice here, it's quite complex. It requires a lot of equations and parameters to use. So we thought, okay, can we do something simpler? I mean, can we model dendritic spikes in a way that does not need to utilize the HH model? And this is exactly what we did. We stripped away a lot of the complexity and we just utilized two channels. I'm gonna go into more detail later, namely a positive channel and a negative channel. And in conjunction, they allow a very good representation of the HH model without needing all these differential equations that I remind you need a lot of compute when you're running in large scales. And here you can see an HH model in comparison, let's say, to a Dendrify model. But if you overlap them, they are very close, although we use much less differential equations. And also, the fact that it's much simpler to, model is also much simpler to validate. So, in essence, here you can see that this here is the voltage of the membrane, and here you can see the two channels that are responsible for the shape of the spike. And when we have a positive current, a negative current, and by selecting the relative amplitude of these two, the timing of these two, and you can see here some of the parameters, and the duration of these two, you can design any type of spike that you'd like to model. And in general, the Dendrify workflow is as follows. First, you design a model as a cartoon representation of the model. It's, let's say, what you have in your mind as a model. Then you express it with some Dendrify code. It's actually very simple code. It's descriptive code. You don't need to be an expert in Python to implement Dendrify. Here you can see here, for example, that to model this three-compartment model, you just go in Dendrify and say, I want to create a soma, an apical and basal dendrite with these characteristics, and then put it all in a neural model. And then after you create your model, you use Brian 2 to solve all the differential equations and with all the goodies that Brian comes to, such as synapses and monitoring and all the advantages of Brian. So let's say to understand exactly what Dendrify does, let's see this toy example. Here we have four compartments: a soma, a trunk, proximal dendrite, and then a distal dendrite. And let's say we want to add some synapses that are going to the distal and the proximal compartment. The way you describe this in Dendrify is as such. You can see it's okay. It might look as repetitive or long snippet, but actually it's very simple to just describe. It's like, let's say, HTML for creating websites. It's just a descriptive code. It's not so hard to learn. And what Dendrify does in the background, it creates all the differential equations and all the parameters that are needed by Brian to run this exact model. So if you didn't have Dendrify and you would like to create a model of this complexity, you would need to write all this stuff by your hand or create your own version of Dendrify and functions or to handle this complexity. And here are some very simple experiments just to show you how its behavior. Here we're just injecting some input current to the distal compartment. We have the local generation of dendritic spikes, and you see now how this perturbation propagates to the other compartments. Here we just injected some current in the proximal, and you can see again a local generation of these spikes. But now this perturbation goes both to the for more distal and to the proximal compartments. This is because of the cable properties. Everything is connected with each other. And here another example, same dendritic spike that propagates again into two directions. And another thing that is very nice is that also with Dendrify you can replicate backpropagating spikes, as I explained earlier. Here, for example, you can see when the soma fires, because we injected the soma with some current, you can see that there are also some dendritic spikes in the trunk, in the proximal, and then some spikelets in the distal part. These spikelets is the sorry, these spikelets are because this is a much more distal compartment. So we have the spikes that were propagated in the proximal compartment didn't manage to reach this distal compartment. And finally, Dendrify is, we're going to see more later. You can access it here. It's in the links I will show you later. It's free, totally open source and documented. It includes a lot of experiments and examples that we're going to see also later. A lot of documentation for whoever wants to delve into it. There's a lot of information there to unpack. And also it's universally compatible. It runs on any operating system, and also through the Brian to CUDA interface, can even run with GPUs. And I can manage even to run some simulation on my iPad, for example. And that's all for now. That's the introduction. So for the next steps, we're just going to explore some tutorials that I already have in the documentation. So I highly advise you, if you want to follow with me, to go into the documentation page. You will find the link in the chat in YouTube, and go to this tutorial one, Dendrify Basics. And also, I would also again highly recommend you to open a Google Colab. Just go and let's say Google Colab here and create a new blank document where you can code on the same page with me. So we're going to have a short break, maybe 5 minutes, to set up some things. And if you want to get the maximum out of this tutorial, just have this page ready and a blank Google Colab document. That's all from me, and let's take a short break, and I'll be back in 5 minutes. Hello and welcome back. So now we're officially starting the tutorials, and before I go into the code, I wanted to show you a bit the documentation of Dendrify because I skipped this part. So uh, if you go in the main page, you will see multiple instructions on how to install Dendrify, some release notes to see what changed from previous versions. You can find the tutorials in this section here. There are three tutorials, two basic and one more advanced. Today we're gonna do the two basic tutorials together. This one, Identify Basics and Running Simulations in Brain 2. The other is for more advanced users that are familiar with the differential equations and how Brian works. And it takes a lot of effort to teach this part because as I mentioned it's a bit more advanced, so we'll skip it for today. And here you will see multiple examples of pre-made code. For example, here you can see some snippets and also the output of these snippets that will help you understand better how Identify works. And also we have added some validation tests, for example, where you can see some very common electrophysiological tests on how to estimate the input resistance of a model, the FI curve of a model, the membrane time constant, and other very well-known experiments from electrophysiology. And here is the reference documentation section, the API, where you can click any single classes in Dendrify. Let's go, for example, in Dendrite. And you can see that if you need some help, you can go in this section here, and you can see all the parameters of each class, all the arguments, and the methods, the attributes, and everything that you might need. And also, since this is an open source project, you can just click here in the source, and you can even see the source code of what happens behind each class. But for now, we're gonna focus here. So in case you want to follow and do some coding with me, just go into tutorials, Dendrify basics, and open this page here. And also page Google Colab. Here I have a split view, where on the left I have this tutorial, and here I have a blank Google Doc. So to install Dendrify, you just go to Google Colab and you click pip install Dendrify. Shift and enter. Shift and enter is gonna run the cell and it's gonna create a new cell to continue coding underneath the previous cell. Um, Give it a moment. This command automatically installs Dendrify as well as Brian2. I mentioned the Brian2 is a basic component of Dendrify. You cannot use Dendrify with the Brian2. So by simply installing Dendrify, it will automatically install the latest Brian2 version. Also, for simplicity, you can simply click this button to copy all the contents of a cell and just paste it here. So copy paste, but then I click shift and enter, and I run this cell and I go to the next one. So there are two main basic objects in Dendrify. We're gonna see them in this cell here. One is the object soma, and the other is the object dendrite. They're very similar under the hood. They do share some similarities, but they also have some extra features. For example, here, when you type existence sum of compartment, you will see that both objects belong to this compartment class, which is responsible for creating the differential equations for each one. And what can you do after you create a compartment like a soma or a dendrite? You can simply go and print its equations. By default, when you create a soma compartment, it creates differential equations of point leaky neuron. And just to understand a little bit what happened here, when I created this soma, you can see that I added this flag here, Soma. I could literally type anything inside it here. I could call it Nick, for example, or cat, it doesn't matter. But this string here is needed to format the equations and have compartment-specific equations. So here, the first row is the membrane equation. Then I have an auxiliary variable. Sorry, I have this variable isoma, which variable is going to be evolved. You are going to see it's going to have more stuff here. And it essentially captures all the inputs that are going into a compartment. And also have this auxiliary variable, I external soma, which is used for validation purposes, or if you want to inject some current to the soma. Let's see also what happens when you print the equations of the dendrite. You see, I have the same exact copy of equations. Oh, let me zoom in. Is it better now? I'm sorry if it was tiny for you. Okay, thanks, Raman, for the feedback. What was I? Okay, when you print the dendrite equation, you can see that it's like identical. But here, instead of writing soma, you can see that it's writing dent. So what else can we do? One thing we can do is just grab a compartment and add a synapse to it. So the way you do this is you just take a compartment, dot synapse, ampa, and then you need the tag. This tag is similar as in the previous case because let's say you have a compartment that has two sources of input and you want to differentiate somehow the equations from different streams of information. So by having just AMPA, we will have a collision of the different equations that they point towards AMPA. So we want something to differentiate between different AMPA pathways that go into a single compartment. But just by clicking dent.synapse, let's see what happened after we print. Okay, you have all the information here, but I like it more if it's interactive and can code together. So here you can see that the previous equations now have been updated, and now I have another two lines of code. Here is IAMPA A dent. What does it mean? It's IAMPA from A, this is the tag that we used previously, to dent. Dent is the number, the name of the compartment that received this AMPA signals. These are the AMPA equations. Here is the conductance of AMPA channel. This is the driving force of the AMPA channel. And this is the S, is the state variable. If it's 0, it's closed. If it's 1, it's open. And this is a weight variable that can be used for plasticity. And here is just how you write exponential decay in Brian 2. You would just, okay, I will not get into more detail. You can also read some comments I have here for you for later. So let's add another AMPA from a different pathway. Now I have pathway B, and you see that yet again the equations have been updated, and now I have another chunk of equations here that is AMPA B to dendrite. And let's add NMDA receptors. It's not so hard. You just type the compartment you want, the channel you want, and the flag to distinguish from possibly other NMDA receptors. And with just 3 lines of code, some that was very small previously has got some substantial size now. And you're going to see that the more things we add, this package of equations becomes larger and larger and larger. But Dendrify does this automatically for you. And what else can you do in Dendrify? You can just add noise. How do you do this? Don't dent.noise. And now we have extra equations for noise, which is Gaussian white noise. I'm not gonna get into details on what this line does, but in case you would like some more information, you can just click here in Brian's documentation of how this thing works. And let's say the reason we developed Dendrify was dendritic spikes. How do you add dendritic spikes? Exactly as all the previous mechanisms. You just select the compartment. You write compartment dot d spikes and then the type of spike you want. Here we just added a sodium spike, for example, in this compartment, and now you can see that the equation package has grown a lot significantly. And here I have some extra differential equations that handle exactly how we modeled the two currents that are responsible for the shape of the dendritic spike in Dendrify. Also here, if you click here, you can find some more information of how dendritic spiking is implemented. Also, this is very helpful. The dendritic spike playground. Again, we have two currents that the properties shape how dendritic spikes look like, and we have infinite control of their shape and the duration and the relative activation, but we can play a bit later with that. Let's focus on the tutorial for now. So, okay, we have one compartment that has all these mechanisms, and also we have a soma. But right now, they're not connected to each other. They are independent. How do we connect them? We just do dendrite dot connect the soma. And let's see what happens now. When you perform this action, you see another line of equations. Now we have a current that is called I, soma, then always in Dendrify. This is a pre, and this is the post. So we have a current, a current that is a coupling current from the soma to the dendrite that takes the relative difference in voltages and a coupling conductance. And also from the somatic perspective, let's say, you have another current that is I dense soma. This is the current from the dendrite to the soma this time, which has exact opposite sign in comparison to the previous current. So the way two compartments are coupled and dendrified, this is also the same in neuron, I think. You always have two currents, one exiting the compartment and one going to the compartment, and in conjunction they capture the coupling that happens, let's say, in biology. And okay, have this section, user-defined equations. Everything I show you here is Python strings. So since it's Python strings, you should be able to handle it. And if you are aware of what you're doing, you can do whatever you want. I mean, this is a huge advantage of Brian. It gives incredible flexibility to its users. So you can see here, if you type what this equations is a string, a Python string. So you can definitely do some default Python formatting stuff. Like here, I can just, this is a tutorial I had in the CNS workshop, that's why you have the CNS. But what did I do here? I simply took the equations of this compartment and I simply appended some strings to the end. Again, you have infinite flexibility to do whatever you wish with these strings. Uh, Provided you know what you, I mean, this is a feature that is more for advanced users. And so far, we discussed a lot about equations, how to create the model equations, but we haven't said anything about its parameters, which is another core feature of Dendrify. If you go and try to access the parameters of this compartment, you're going to see a lot of errors. Warning, missing, could not do this stuff, could not resolve this, could not calculate that. This is on purpose. If something fails, then it's designed to fail loudly, because I don't want any hidden errors that are not discovered by Python to get inside the model. So if something is missing or if it's not properly implemented, you're going to find out. And this is the first layer of protection, let's say, and then Brian adds another layer of protection later. So we're going to see how we pass the equations. You are going to see also that here we do have some default equations. For example, we have the reversal potential of AMPA, epsilon AMPA, or alpha, or the magnesium concentration. This is required for NMDA receptors. And Dendrify does come with some default parameters, which you can access by just going to dendrify.default parameters. These how I imported Dendrify in the beginning. You see, I did import Dendrify as D. So now D means Dendrify.default params. And you can see these default params. And I use some very common values from the literature. But in case you don't like these params, you can always adapt and change the default params and update them. Sorry, what's happening? Okay. And now, for example, you can see that I changed reversal potential of calcium, and I made it 2024. It doesn't matter, it's just a random value. So Dendrify does come with some default params that are very common in literature. You also have the flexibility to change them. So what about the properties of the compartments? Every compartment Dendrify is treated as an open cylinder. So what does a cylinder have? It has some length, has some diameter. Let's copy paste snippet here. So it has some length, it has some diameter, and also now we start using some biophysical properties such as the specific capacitance. This is the capacitance of the compartment per unit area. Also the leakage conductance of the compartment per unit area, and also we have the R axial. This is the axial resistance. This is how much the currents attenuate between two compartments. And this is the V rest. This is the rest potential of a compartment. These are some very common values in the literature as well. This is just an arbitrary value. Don't overstress. This is just a tutorial. It's not about biological realism. I just want you to understand what can Dendrify do for you. And now if we print Soma, by the way, you can simply print the compartment. You don't need to print every single attribute in isolation. You can just go to a given compartment and print it and see everything that this compartment includes. For example, here you can see that Soma has these equations. It has these parameters in alphabetic order, and also all the parameters that are user-defined, what we included here. And also you see that when you print the compartment and it's correctly developed and everything, there's nothing missing, now there are no more errors. Whereas previously, when we tried to access the parameters, for example, we had a bunch of errors. Now they were gone. And this is a very good sign that, okay, maybe we're good to go. What other can we do with Dendrify? By default, we can access the surface area of the compartment. You can see here it calculates automatically the surface area based on the formula of open cylinder, because we have the diameter and we have the length. We can calculate also the surface area. We can also calculate the capacitance of the compartment, the absolute capacitance, the absolute leakage. Okay. This is how we introduce some parameters for the compartment. What about the synaptic parameters? Previously, I showed you how to add the equations for AMPA, for example, but I never explained how to add the parameters for AMPA. It's simple as that. You just type the compartment of your choice, synapse again, AMPA, and now the tag I mentioned to distinguish it from other AMPA channels. And now you want the conductance of this channel and the tau decay of this channel. How much fast this channel closes and after it's been activated. And this is the decay time constant. This is exponential decay. It's not total duration. So you can see now that again, all the equations and the parameters have been updated. And we also have now this here, which is the tau AMPA decay. What else? What else? What else? Okay, something similar again for the NMDA. That's also something very interesting for you. So, some channels don't always have only a tau decay, but they have a slow opening. Especially this is very common with NMDA receptors. Although it's very common for simplicity to only use tau decay for the kinetics of a channel, if it's of interest for the experimenter to also use tau rise, they can use tau rise. So when you create, let's say, an NMDA synapse in a compartment, you can set its conductance and a tau decay. And in addition, if you want, you can optionally add a tau rise. However, this is going to have a huge effect also in the equations. For example, here in NMDA, you will see that we have two rows of differential equations, whereas in NMDA-B here we have three rows of differential equations. The reason is that to model a channel that has both rise and decay, we need a sum of two exponentials. And Dendrify cleverly handled the fact that here we also have a rise with a decay and use a different set of equations to model this slower NMDA receptor. So this is another thing you can do in Dendrify. Also here, the noise can get some parameters as well. It's a Gaussian white noise, so it has a mean, it has a sigma, and a tau. Again, if you see the Brian example I showed earlier, you can understand what this is. What else do we have? The dendritic spike parameters. I didn't mention this at all. So to learn how, what am I writing? I'm just following the tutorial with you. I'm not prepared, fully prepared. We're going to see this later. This is more complex. So what else do we have? We have the coupling parameters. How do you couple two compartments? You can just connect the compartments and set the coupling conductance. That's all. All it takes. Okay. So another way that we model simplified compartmental models is that sometimes we don't want to use too much biology and set specific capacitance and leakage and dimensions. We just want the model running. And we don't need all this biological complexity. So Dendrify allows also to set the capacitance and the leakage in absolute terms. For example, here we have a different notation. Instead of using CM and GL, we have CM abs and GL abs, and now we have different units here. Now we have fixed picofarad, not per unit area. And Dendrify allows this as well. So here we don't have the notation that it's an open cylinder. It's just a dimensionless compartment and has these fixed properties. This is something that the user might need and to avoid the complexity. The problem with this approach here is that if you try to automatically connect these two compartments, you're going to have a lot of errors. The reason is that since these two compartments are dimensionless, Dendrify doesn't know how to connect them. So you always need to add the coupling conductance. If you don't have if you don't have the dimensionless compartment, you can always connect them because Dendrify does the assumption that they are open cylinders, so it takes the half resistance between the two cylinders. But if we don't have values for the cylinders, we cannot do it. So the only option to connect now two dimensionless compartments is to just set a fixed coupling conductance. What else? Okay, last but not least, this is the end of tutorial 1. Many users reported that I didn't have point neurons to Dendrify, and that, okay, we need point neurons as well, because sometimes when you create a network of pyramidal neurons, you might want to use some simplified interneurons inside this network. So although it's super easy to create a point neuron in Brian, they wanted to do it in Dendrify for consistency. So Dendrify has another class. It's the point neuron model class. So it does exactly what it says. It just creates a point neuron model without dimensions, without compartments or anything. So this is the last the end of tutorial 1. We're going to have a very short break, around 5 minutes, before we go to the fancy tutorial. Tutorial 2 has to do with simulations and how to interact in Brian and how to connect Brian with Dendrify. We're going to see some more fancy stuff, I promise. Let's have 5 minute 5 minute break and yes, see you in 5 minutes. So, hello everyone and welcome back. Now for the next tutorial. Again, it's optional, but if you want to code along with me, you can just go to Dendrify documentation and click here, running simulations. And what's happening? Okay, that was already there. And I would like you to have uh, a new blank. Okay, a new notebook. Why? Sorry. What? Can I just have a new one here? Okay, it's here. Okay, I was expecting it to be simpler because I have the split view. It doesn't matter. I'll just go here and collab. Let's go nuclear solution, a new one. Just retype in your search in your bar collab.research.google.com, new notebook. Okay, I was hoping I could replace the previous one. It didn't work out. It's okay. So again, install both Dendrify and brand pip, install Dendrify, and then press Shift Enter to run this cell and go to the next one. Wait a couple of seconds, install everything that we need. And also, okay, copy this cell with some imports and some preferences, and then paste here, and then Shift Enter, or you can also click here, this if you want. This is one setting for Brian. Brian allows to compile code in C++ for much faster simulation time, but also compilation takes time. So for simple codes like the ones we're having now, just using the NumPy version, the Python version, is fast enough. We don't have the compilation overhead. And also, this is just for visualization purposes. Just copy paste this again, Shift Enter, and now we are ready to start. This is a model I described also in the initial presentation. Our goal in this tutorial is to create a 4-compartment model, one that has a soma, a trunk, a proximal compartment, and a distal compartment. The proximal and distal compartments can have AMPA and NMDA synapses. And the way you describe this in Dendrify code is such: you create soma, dendrite, which is trunk, dendrite prox, and dist. Again, the names are arbitrary here. I can call it whatever. I just use some names that make sense based on what I want to model. And then we add the synapses we want like that. So the distal has these synapses, the proximal has these synapses, and I connect them using some fixed coupling conductance. So let's do this. Okay, it's fun. This is super fast, doesn't take any time to simulate. Um, okay, so what if, okay, now it was simple. We didn't have many compartments to model. What if we had 10 compartments or 15 compartments? Are we gonna do, again, connect, connect, and connect? It's gonna be a lot of repetitive code. In Dendrify, there's a much more elegant to create a compartmental model, and you can see it here. So you first define the compartments again, then you can add any synaptic pathways, and then you can simply create the graph-like representation of the compartments and the coupling conductance. So here I have a list of tuples. The first one is the connection between soma and trunk, and this is the strength of the connection. Trunk prox, prox this, etc. And then these are some shared parameters that I would like to have between all compartments. For example, in the old school approach, I used to have a lot of repetitive properties such as CM, capacitance here, 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 and here 4 times. But if you have a neural model, you can just write once, and this is going to be a common property for all compartments. So with less line of smarter code, you have the same model. Okay, we created now the cool way, the new neural model. Now we can just, like any compartment in Dendrify, we can just print it and see what we have. So these few lines of code generated all these things here. So you will see that all the equations are grouped in small paragraphs, let's say. Each chunk of equation is designed to represent specific compartment. This is a summa, this is a trunk, this is the proximal width, the synapse is included, and this is a distal. And again, we have a dictionary where we have all the parameters that were created in alphabetic order. And we have something that is going to make sense in a while, events and event conditions. So what else can we do with a neural model? We can queue it. So if you go to a model and then type .asgraph, you can see a graphical-like representation of that model. So we have, again, 4 compartments, and that's how they are connected. This is mostly to validate that you did everything correctly and you connected the compartments in the correct order. If you saw here soma and then dist and then prox and trunk, you understand that you did something wrong. So it's a good step to verify yourself. And in case you want to export this model and, I don't know, to show it in a presentation, or you like it, you can also customize this view. You can scale the nodes, you can change the colors. There are a lot of options, but you can find them all these in the documentation. So this is mostly where Dendrify ends, and now where Brian starts. So just before we start using Brian, by the way, I didn't mention anything about Brian 2. In case you would like to use Dendrify, I highly, highly recommend you to go to Brian documentation and see the tutorials, these 3 tutorials. They are gonna be help you a lot in understanding what Dendrify does under the hood, and also it's gonna help you speed up a lot of things in the process as you create models and you want to run simulations. I didn't cover Brian at all today because I didn't have so much time, but in case you want Dendrify, I think Brian knowledge is a basic prerequisite. So highly, highly recommend. They have very nice tutorials and they have an incredible documentation. If you go to examples, all these are codes that are ready to use, and you can do everything. For example, how to model STDP or what else? Anything. Someone asked earlier about astrocytes. I think they have also done something about astrocytes here. So take a look. Take a look. Highly recommend it. Back to Dendrify now. So we created the model Dendrify, and this is how we export it into Brian 2. Brian 2, the core object in Brian 2 that is responsible for neuronal simulations is the neuron group. So we grab the model created with Dendrify, we add dot make neuron group, and then we add some some parameters required from Brian. For example, here we can set the threshold for spiking. We can set the reset, what happens after the spike of the soma. And here I have done another trick that is a Dendrify trick. Because we don't use the Hodgkin-Huxley equations, when a typical leak integrated fire model, whenever it reaches a spiking threshold, it just resets. So we have the crossing of the threshold, and then we have a reset value that is closer to the rest potential. However, this is not a biological property. Real neurons do spike, and when they spike, they go to more depolarized, more positive voltage values. So in order to capture this, we use a dual spiking mechanism. What does it mean? Simple as that. We just go to a first, when you have a second, the first reset takes the membrane voltage to a positive value, and then the second reset takes the voltage to a more negative value. And we can also set how wide this spike is. In case it doesn't make sense, we're going to look at an example later, and hopefully it will make sense. But this is needed to simulate more realistic somatic spiking, which is also responsible for the generation of backpropagating dendritic spikes. So in case you want to capture backpropagating dendritic spikes in your model, you will need this dual reset mechanism. And now we have left the Dendrify territory. We are only Brian territory now. And let's say we want to run a simulation and record what's happening inside the neuron. So the variables I want to record from is voltage with the soma, the trunk, the proximal, and the distal. And this is how I create a state monitor in Brian 2. Uh, sorry. Okay, and let's run a simple simulation now. The protocol I have right now is I run the network for 10 milliseconds. I do nothing. Then I inject some current, some external current to the soma. Then I run the simulation for 100 milliseconds. And then I remove this previous injection and I run another 6 milliseconds to just let it go closer to the rest. And here, let's visualize the simulation result and see what happened. You can see this is what I was talking about earlier, that when the soma spikes, we do not have a simple reset. We have a real voltage increase like the biological neuron, which also allows the dendrites to follow along and also generate spikes. Here we don't have dendritic spikes so far, so this is what happens when you have passively connected dendrites, but this is also happening biologically. When the soma spikes, the ions that go inside the soma, they also um, go to nearby dendrites. They work as current sinks. So you also have an effect like this one. Let's zoom in a bit. Okay, now you can see in high resolution what happens, the order of events. We have the spike at the soma, some passive dendrite that follows the spiking, and because of the voltage attenuation, the distal compartment doesn't feel much of the somatic spike. So let's now create a network with some random Poisson input. This is how you create some Poisson input in Brian 2. You just use the Poisson group, and here is how many neurons you have, and this is the frequency of each neuron. And okay, what else? Let's run this part. Okay. Okay. So I showed you how I created the input in Brian, the Poisson group. This is how it works. And I showed you how I created the model in Dendrify. But there is a fine detail that I didn't explain so far. How does this input become a Dendrify property? Uh, to understand this, let's first see the equations of the distal compartment. You are going to notice that, let's focus, for example, in the AMPA compartment, sorry, in the AMPA receptor, we have this ds AMPA path x slash this, okay, this is the state, S here is the state variable of this AMPA channel. When this is 1, it means it's activated. When it's 0, it means it's closed. So, how do we make Dendrify to understand that this Poisson group needs to activate the state variable here, and we then to create some AMPA currents that go inside the distal dendrite? It's not so hard. We just use the Brian synapses object. This is the input, the Poisson input we created here. This is the group we created here, the neuron group, and this is here we define what happens every time a presynaptic input arrives. So here, whenever a Poisson spike arrives inside the neuron group, which is a dendrifying model, we're going to have this state variable to be incremented by a positive value. I set it here 1, it can be whatever. So every time a presynaptic spike arrives, this S becomes +1, and also NMDA as well, the same. So this is how the brain input becomes Dendrify input. And now I connect this also with some probability. Okay, let's run this code, some simulation code again. So now I created a spike monitor. This is also whatever you see with B is a Brian object. Whatever you see with D is a Dendrify object. So I just created a spike monitor now to see the raster plot of this simulation and see how the network was activated. And what else? Let's see also a sample neuron. Okay, you can see that how the somatic and the dendritic voltages evolve over time. And let's add some dendritic spikes and see what changes now. The values I'm using here are with trial and error. I just wanted something that looks good. It's not a biophysical property in any way. And in case you want to use Dendrify for real purposes, I highly recommend you to play a little bit with the values and achieve a dendritic spike amplitude that is closer to the biophysical one. I can show you later how you can do this. And let's add some dendritic spikes. Now I'm gonna have three dendritic spikes, two different, essentially it's the same dendritic spike, same name, and they have a different rise and fall conductance in every compartment. Okay, I add the dendritic spikes. And what else can I do here? This is here again, I create a neural model as previously. And now another thing I can do after I introduce some dendritic spikes in the model is that I can configure them. So an easy way to have common properties for each dendritic spike type is to have model.config.spikes and then the name of this spike, and then add a common threshold, common duration, common offset, common parameters. So here, Dendrify is going to read each compartment and see this specific event. It's going to add these parameters here, or from here. Sorry, where is that? Yes. And everything that I added inside config the spikes is going to be a property of each individual compartment. In case you had another dendritic spike, let's say I didn't call it the spike, I called it sodium or something like that, and I wanted this compartment to have different properties, then I had to use another config the spikes, where instead of this spike, I would have sodium inside there, and then here I would specify the properties of this channel. So here, this config the spikes, let's say allow us to configure channel-specific properties that are common between all compartments. So I run this, okay. Let's print the model, okay. So this is all the code that was needed to express this model. A lot of stuff going on here. And also now you can see that we have some extra events. We have the spike, and this is the name of the spike, and this is the compartment. We utilize the custom event functionality of Brian to simulate all the events in Dendrify. And this is the condition when this event is triggered, when the voltage is surpassed, and also I have the refractory period has surpassed, then it's allowed to spike. What else is important to mention here? Okay, let's run the simulation now, like before. See what changes. Okay, I run my simulation here. Now let's focus in one neuron. You can see now in the previous example, when I focused in one neuron, you could see that I didn't have the dendritic spikes. The dendrites were just passively following what was happening at the soma. But here you can see it's much You can see a very different profile of the dendrites, but to make sense, we need to zoom in first. And now you can see that after every somatic activation, I have first the trunk being activated, then the proximal compartment, and then the distal compartment. These are the so-called backpropagated dendritic spikes that are initiated from the soma, going backwards to the dendrite. And what else? See, okay, I was here for this final part. I'm just adding some noisy input. And okay, I don't even know why I print this in the same mode like before. Okay, so yes, I remember now. I'm sorry. Here I was using fixed current injection to the soma, and I wanted to see what's going on the dendrites. Here I'm just injecting some random Gaussian noise in all compartments, and then see how the dendritic spikes result in somatic spiking. So let's say I run this, you understand now. So uh, here you will see a much cleaner image because here I was using a lot of current, very strong current injections, and I was holding the membrane high. Whereas here you can see that how the neuron responds in response to some noise injections. And if we zoom in as well, again, you'll see this image. It's like the previous protocol, but instead of using fixed current injections, I'm just using some noisy input currents. And again, let's also see something with the point neuron model. This is a final simulation I want to point out. Very similar code to the previous, we just use a point neuron model. Here you notice that we don't have somatic spikes. This is a typical leaf behavior where every time the threshold is crossed, we just have a reset and no other voltages because this is a point neuron model. So these are the two basic tutorials. Unfortunately, I don't have endless time to go into very, very fine detail for every single class and everything. But after you're done with these tutorials, feel free to play around with the documentation. And in case you have any questions, you can ask me later in the Q&A session we have. And always you can text me and email me in dendrify@dendrites.gr or open a new issue on GitHub. I honestly prefer just an email. I receive a lot of emails on a monthly basis, so I would be glad to help you and solve any questions or help you with the projects. And Aman, how much time do we have left? Okay. In 5 minutes, we're supposed to start the Q&A, so we have a little bit of time to play around with an example. Another thing I want to show you is the Analytics Spike playground, which is like a standalone graphical user interface that will help you design, let's say, the dendritic spike of your dreams. Unfortunately, if I try to run this in Google Colab, it's a bit slow, but I already have an example locally in my machine to how it's running. So I just copy pasted. I literally just copy pasted the example here from the documentation. Of course, I have already installed Dendrify locally, and when I run it, it takes a second to compile some brand stuff. And sorry, it opened in a new window. Now, I guess you can see this view here. And what you can see here is by using these sliders, you can change the properties of the two channels that are responsible for the shape of the dendritic spike. For example, here I can change the rise conductance, the positive current conductance, and now you can see that this neuron becomes far more excitable. This is similar, let's say, to the conductance of the sodium in the real neurons. the widget.
I see your presentation.
Oopsie. Have some technical difficulties. I lost the widget. You can see my presentation, you said.
Try to close the presentation.
What? Sorry. Now? I'm sorry for that, guys. Didn't expect that. Oh. I have no idea what's happening. It's okay. Okay, I think this is an OBS bug. This is software we're using to make this stream. Let me check that. External monitor, properties, and display capture. Okay. I don't know why you can't see that. Oh, I'm sorry, guys. So I don't even have the presentation there.
But now this is the window that
Yes, the window has frozen. The image has frozen for some reason.
try to hide it and then there.
Which one?
The pan thing.
This one.
Yes. No.
But in OBS it works. It frozen the stream for some reason.
Ah.
Yes, you can see it here. Okay, let me try something last. I apologize for that. I'll just change the display. Okay. Okay. Display, let's go back. I think it's a bug. Display capture, okay. No?
Okay, try and type it.
I think you see the documentation. Okay.
Everything is fine.
Everything is fine.
Yes. It was fine.
My colleague was boycotting me. His screen was. It's okay. This happens. Sorry for that, guys. Hey, guys. So here you can see the Dendrify playground. Okay, let's make sure. Raman, is it working? Great, amazing. So we had some technical issues, sorry. So here you can see we have the two different channels that are responsible for the shape of the Dendritic spikes. Again, with these sliders, you can select, be careful here, they might look identical, but the axis values are changing here on the left. So by changing the slider, I can make it more or less excitable. I can also change the duration of the rise. Now I can break it. Also, I can change the duration of the fall. I mean, okay, it was very good before. Now I broke it. I broke my code. I can change the offset. Notice this on the bottom, how these currents change and how they affect the shape of the dendritic spike. Also, I can change the refractory period. I can increase it or decrease it and ruin everything. That's all. We have some extra properties you can change here. I mean, these are some defaults. In case you want to adapt it for your specific user scenario, you can just go here and change the capacitance. It's going to affect the tau membrane of your, the dynamics of the membrane of your neuron. That's all. It's also, this interface is also highly customizable. You can just go again the documentation and see all the various options you have. Where is that? Here. The documentation, you can set all the default parameters, change them, and play with it. What else? Okay, highly recommended to take a look at all these different examples that we have here. You can see the validation tests, you can see the various models that are available, things you can do. We also have a math library here where you can also read about the models that we have included in Dendrify. That's all I had for now. If again, if you need some support, you can email me here. And if you find some any known issues, you can also email me so that I have some add them here. So far, it seems to work stable. Thanks for your attention and thanks for being here. I think Raman will set up now Google Meet, where everyone is welcome to join and ask me any questions that you might have from today's presentation. Um, Raman, have you started Google Meet? Yes, a second, please. Is it ready?
Yes, yes.
You share the link?
Yes, I sent
Okay, so please everyone join the link in the chat. And I don't have the link.
it's in the back.
I don't have access to the chat. Um, okay, give me a second. I will find it, don't worry. Oh, thanks. Okay, I hope you enjoyed the tutorial. I'm just going to close the stream and join in Google Meet. See you there. And yes, see ya. OBS.